is visible, and let's start now.
Okay. Hey, you can see my screen, right? The presentation.
Yes, yes.
Okay. So today's agenda will be to go over all these basic algorithms which can be done using all the components we have learned so far, like loops and if-else condition. So first algorithm we will see, like today is like a case study class. So basically we will go over all these simple algorithms and try to code them in Python. First of all, understand the logic behind it and then code it in Python. Um, so let's go over the binary. Okay. So binary conversion is just like this, right? So let's say I have a number 12 and I want to let's say convert it to binary. So I will divide it until I get 0 or until I get 1, right? So like 2 6 2, 6 or 12. So now the remainder is 0, right? And then you can divide by 2, 2 3 is 6, again remainder is 0, then 2 1, remainder is 1. So now I get a number less than 2. I stop there and the binary conversion is like 1100, right? So, if I want to code this in Python, it should be something like this. Yes. Just increase. So I have the number a equal to, let's say, 12. I will divide the number with 2 until I get a remainder less than like until I get 1. Right? Okay. So while a modulo 2 is greater than, no, divided, right? So print a modulo 2, that is the remainder, and at the end print a divided by 2. Sorry, I forgot to restart. So, so because this a is not getting changed, right? So I have to do a equal to a divided by 2. So, like what is happening is it's printing the remainder and then changing the value of a. That means for the first iteration it will print, let's say the remainder will be 0 and the a value of a will be changed to 6. Again, this loop will continue until the resultant is less than 2, and lastly we print the resultant. One, and here before quitting this, we should also print the remainder. So this is how you can convert a integer to a equivalent binary with only while loop. Like this function is already there in Python, that is bin. Bin function represents the same thing. Let's say bin 12. It will give you a binary string. 0b means binary, and then 1100 is the equivalent binary number, and it returns a string. Okay. Now let's go to the next algorithm. So guess and check. Guess and check is what? So let's say I have to guess. Like someone has assumed a number between 0 to 100. Let's say I want to guess that number. So there are three ways which are like let's say which improves on one on the other, right? So the guess and check is just like random checks. So if let's say if I just like guess random numbers and try to check whether it matches with the assumption of the other person. So that is one algorithm, and then improved one. So little bit improvement. So because we are guessing randomly for the first case, it's not that much efficient, right? So so the so one improvement could be to like start with the lowest number and increase one by one until you get the highest number. That is linear search, right? So that actually has a upper bound. So we have to at max search in numbers, and it is surely will get the assumption whichever the other person is made. Right? So okay. So we'll just implement the guess and check first and see how inefficient that is, and then we'll move to linear structure. So for a let's say for a visual representation, this is something like this. Let's say we have a number from 0 to 100. And somebody has picked a number here, right? Let's say this is 60. If I just randomly check here and there, right? So it will take a lot of time. The probability of getting here like 60, let's say 0 is exclusive, so it will not take 0. So the valid number is from 1 to 100 in this range. So if I just randomly check here and there, the probability of successfully reaching to 60 is 1 over 100, right? So there is one instance where we can successfully guess that assumed number. So so at least we have to guess for 100 times. Like in expectation, we have to check for 100 times. Then we will successfully get 60, right? Because like the total probability would be 1 almost, but not always. The statistically it would be more like statistically it is 100 times you have to check, but in practical it could be more. Let's say we have to check in practical we have to check 150 times to reach to 60. Okay, so just implement this. Okay. So let's say the input number is 1. Assume number is let's say 60, and we assume that how many guess and checks will be required to reach to that 60. Okay. So while let's say we'll take an input, or will not take an input because it will slow our computation for 100 times for I equal to 1, I less than equal to 100, I plus plus. Oh, sorry, this is C syntax for I in range 100, right? 100. So it will loop until 100 times, right? Loop until 100 times, and we will check. So the to to get a random number between 1 to 100, we have to import a package called random. Now, what random gives you is a number between, let's say I can random random integer, and if I check the limits, it's like inclusive, right? 1 to b, including both the endpoints. So if I give 1 to 100, it will give me one random number. Okay. So this is the guess. Now we will check after how many guess we reach 60. If guess is equal to 60, print I. So after this many checks, we reach 60. And actually, not actually I, it's start I from 1 to 101. So 101 means it will run from 1 to 100, not including 101. And then if I don't find that within that range, within 100 iterations, I will say unable to guess. Oh yeah, and let's say we want to this will take. And so one thing, there is a concept called for else loop. So if the loop doesn't break, if it ends normally, right, then the else block for else one. Let's say this one. Yeah. So else block will only run if it is if the loop is not break. So else. So because it finds, say, the assumption in IPR. No. Finds assumption in 25. So unable to guess doesn't gets printed. 83, 17, 99, 1, unable to guess. So you see sometimes, so the upper bound is not clear. So statistically you should have 100 iterations to reach to that point, but in practice it could be less or more, right? So this one doesn't guarantee you how quickly you convert to the solution. Okay, statistically it will be O of n. The time complexity will be open. So you have to check n times until you reach the guessed solution. However, if we just want to make this algorithm more reliable, then you have to go for the linear step. That's one step improvement over this algorithm. That is, we will check over all the, let's say from lowest to highest, we will check over all the values, and whenever we reach the guess, we just, let's say, stop. So for example, so it will be more intuitive to understand if I just do this. Let's say guess, print. It should look like a game. Guess is guess, and we will take input from user. Let's say input. Correct. Yes. So y or no. Now we'll check if input is equal to 1, and let's say someone can give capital Y as well. So what should do? Input is equal to capital Y. So now look like this. The guess is 5. Let's say I have 60 in my mind. So I will say no, right? Guess is 79, no. Guess is 82, no. This is 30, no. 31, no. 99, no. 68, no. 52, no. 25, no. So until I get to 60, right, I have to like keep this no, 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 no. And when I reach, let's say 60, so this is, you see, totally random. But statistically, after 100 runs, I should get 60. 54, 92, 51, 54, 51, 61, so close. 61 again, 3, 12. Yeah, I get the point, right? So until I get guess equal to 60, we'll just type in no, and then when let's say the assumed is 43, so I will get yes. So it's to find the assumption in 35 iteration. Yeah. So this is like totally inefficient algorithm to what this one is like primitive one, which you can do for check guessing and checking someone assumption. So next would be to find the assumption in a linear fashion. So we'll do so that algorithm would look something like this. We'll do until, so let's say the okay, let's say the initial point is 1 and the maximum point is 100. Someone can assume any value within this interval. So what we can do, we can increment, and the let's say the assumed value could be only integers or whole numbers. Okay. So the value is x. So we can increase one by one and check. This will guarantee you that within 100, with less than 100 iterations, you will definitely reach the assumed value. So this is called linear search. LINEA, linear search. How you can implement it? It would be something like this. Let's say I can copy the same code block. Only the randomness would be replaced by first block. So initial value is 1. Say instead of random, I can do initial. So guess is first initial. Check whether that is true or false. And if it is true, okay, fine. If it is false, so if the loop doesn't break, then we will increase the initial. Let's say initial value should be increased by 1. Right. So within 100 iterations, we reach the biggest value. Let's say I guess let's say 10. Right. So guess is 1. No. This is 2. No. This is 3. No. 4, 5, 7, 9, and then when I see, I guess 10, right? So within 10 iteration, it reaches to my final score. So yeah, so find the assumption in 10 iteration. So this is linear search. So the main benefit from the guess and check and linear search is something like this. So in the previous case, it was like random, right? So the based on the which run you take, you can get more than or less than 100 iterations. So the maximum time limit, maximum iteration is not fixed. It's probabilistic. It's like within 100 iterations, you will reach the assumed value statistically speaking. Okay, but it's not fixed. It can be more than that. So when you have to have a, let's say, a stronger upper bound which doesn't change, let's say you have to have guess the assumption within 100 iterations, then linear search is a better option. But the previous one, the guess and check method, has statistical time complexity of open, whereas the linear search also has time complexity of open. Okay. Okay. Now we can improve, like go to a bit advanced algorithm. So binary search is something which builds upon these two, guess and check and linear search. So what it does, so let me just explain the algorithm. Okay. So the assumption here, so previously we don't assume anything, right? We don't assume that the numbers are sorted. So instead of 0 to 1, it could be random, let's say balls, right? Balls of, let's say, different colors, or let's say different shapes of objects that could be also placed instead of 1 to 100. These two algorithms will eventually work on them too, right? So they don't assume that the numbers have some property, but other objects on which we are kind of doing the game, right? So on which we are guessing have they assume they don't have any relationship among them. However, binary search has a assumption. Binary search assume that the numbers are sorted, or anything, let's say any objects, those are also, let's say, they are sorted by size. Okay. uh, so there has to be some relationship by which we can order the objects. It should not be only numbers, it could be, let's say, based on size, based on weight, all these things as well, if you're talking about objects, right? So let's take numbers for this case, 1 to 100, same thing, but they are sorted now. Previously also took 1 to 100, by chance they were sorted, but that's not required for those two algorithms. For this one, the assumption is xn should be greater than xn minus 1 and less than xn minus n plus 1, and this could be equal. Okay. Or let's say for easier understanding, we can remove the equal or not. Okay. So now what it does, um, it first, so you see, we can, so previously we have only one query, whether the guess is true or false. Now because this is sorted, we can also ask the user, or ask the let's say participant, whoever is assuming the value, about whether the guess is larger or smaller than his assumption, or his or her assumption. So that is one thing which, that is one input from the user which improves this algorithm by quite a lot. Okay. So what we can ask. So previously we are only asking whether the guess is correct or not, right? So now this was the first question. Second question, we can, here, because this is sorted, we can ask is whether the guess is greater than the assumption, or third, whether the guess is less than the assumption. Based on these two, we can channel our search algorithm. So first of all, what we can do is we can take the mid. So the algorithm flows like this. We can take the mid, say 100, the mid is 50, right? And then we can, let's say, we ask the user whether 50 is, let's say the user guess 30, okay, 30 is the guess. Now we can ask the user whether this 50 is less than or greater than the assumption. So we will say that okay, this is greater than the assumption. Now what you can do, we can take mean from 1 to 50. So all this, because we already know that the guess doesn't lie between this range, we can ignore this range. We can only search here now, right? Now again we will do the same thing. Let's say 0 to 50, take half, 25, right? Now 25, we will check whether the guess whether the guess is as greater than or less than the assumption. So the user will say, okay, this is less than the assumption. So this whole range will be uh, let's say ignored in the next iteration. Now we'll take the half again. So 50, 25, 50. What is the half? It's like 25, 50. That is 25 values. So we'll take, let's say, the ceiling value. Okay. So 25 plus 50 divided by or let's say the floor value plus 5, 7 divided by 2, and that's floor value equal to what, 2, 17 point which one, yeah, this, right? So now we can take the floor value 37. Now again we will check whether the guess is it's greater than or less than the assumption. So now it is greater than, right? So all this right side values will be ignored. We'll check between 25 to 37. So you can same logic, 25, 37. If I add them, it is 2, 1, 5, 6, 62 divided by 2. Ceiling value, the floor value is like 31. 31. So now again same thing, this part will be ignored. We'll look here. Now 25, 31, 25, 31, 6, 6 divided by 2. Oh, sorry, 6, 5. 28. So now we have 28. The guess was 30. So this is less than. Oh, sorry, yeah, this is less than, right? So we'll ignore the 25 to 18 this part, and now the iteration will go up to 28 to 31. So 28, 31, 9, 5 divided by 2. It's like 2. Look at 2, and then here 29.5. Now the value is 29.5. See, we're really close, right? So because 29.5 is also less, so we'll take the floor value, right? So it will be 29. 29. Now this is also less than the guess assumed value. So we'll ignore the 28 to 29 quantity and we'll check here until 29 to 51. So 29, 51, 0, 1, 6, right? Now if I take the division by 2, it will be 30. So we'll reach 30. Here we'll ask the guess, ask whether the guess is correct or not. I will say okay. So you see here we are kind of reducing the search space by half, right? Now the time complexity for this algorithm is like O of log n, log previous. Okay, so this is much more efficient than the previous one. So let's implement this one. can implement it for this is the low and high we first initialize low and high. These are 1 and 100. And guess we have a guess. Let me say we assume the number is 30. There are three. It's a while. While. So it do infinitely. Now we'll ask. So the case will be case is int. Int means float. Right? It's truncate the floating point variable. So int low plus I divided by 2. Or instead of doing this, we can also do integer TDC. Double slash. So now this is our float. We add the lowest and highest point values and then take the float. Right? Now we'll ask the user for its input. So input correct type 1 greater type 2 lesser type 3. Okay. And because we are getting inputs in integers, right, 1 2 3, we can pass it to input. Now check. Okay, so if input is equal to 1, that's correct. That means we have already guessed the assumed value. So great. So int, and we can also have a in how many iterations we reach, right? Start I from 1 and finish here. Okay. Guessed. Guess is guess. Guess in ITR I and wait. And if it is not correct, if the guess is not correct, say leave input equal to 2. Let's say the input is greater. Input is greater than the so the guess is greater than the assumption. So what you can do, you can change the high, right? Change the high. So it's like we are ignoring all the values from the guess to the high. So you can move the high to the guess. So we ignore the right side. Input equal to let's say 3. Then we are so it's lesser than the, so you will be ignoring all the values less than the guess, right? So the low will be guess. So that's so now this is the so now we have to do one thing, we have to increase the I to check. So after each iteration I will increase. Now let's say we assume 30. So first case is 50. Is it correct? No, it is greater. 25, it is lesser. Now 37, it is greater. 31, it is greater. 28, it is lesser. 29, it is lesser 30, it is correct. Yeah. So after 7 iterations, we reach 30. Okay. So yeah. So binary search is more efficient than the previous two, guess and check and linear search. And by quite a lot, right? So you see, for let's say for linear search, if I just want to go up to 30, it would take 30 iterations, right? So it will improve from 1, 2, 3, 4 like this. So it will take up to 30 iterations. But for the guess and check one, we cannot say. We cannot say how many iterations it will take, right? It is so it's like it's based on the maximum possible numbers you can have, right? So it will take at max, so at max the maximum possible number time statistically. It can be more than that as well. Okay. So okay, now this is done. Okay. So searching algorithms are done. So these algorithms can be done with loops. So that's why these algorithms are taught at this point. Now approximation algorithms are there. One is how you can approximate cube root. So you see Python have a really convenient way of getting powers, right? Let's say 2 to the power 3. So I can also do 2 to the power 1 by 3. That will also work. But algorithmically speaking, let's say how Python can approximate the solution. We'll later show a generalized way. So this solution, right? A by b to the power p by q. How we can approximate this any value of a and b and p and q could work. So we can approximate any type of power operation. Uh, so now first one could be to approximate x to the power 1 by 3, right? So how you can approach this problem? X to the power 1 by 3. Let's say I have x equal to 3, right? So 3 to the power 1 by 3 is equal to how much? So we can assume that this variable is y, and now power operation is widely available, right? Power operation means 3 time multiplication. So we cannot represent 1 by 3 to the power 1 by 3, but we can represent 3 to the power 3, right? 3 to the power 3 is like 3 into 3 into 3, right? So what we can do, we can power both the sides with 3. Now 3 equal to y to the power 3, right? So y is equal to 3. Yeah. So now what I can do, sorry, yeah, y equal to 3. So now what I can do is I can start from a really low number, let's say 0.0001, and increase by a little bit and check whether the 3 multiplication is close to 3 or not, right? So this is one way of getting y. Uh, right? So the algorithm would look like something like this. So let's say the initial value of y is equal to 0.001, and the increment is 0.001, right? And we will check whether y times y times y is close to 3 or not. So we'll check until the, let's say, the error epsilon error is 0.0001. So we'll check until this value. Okay. So until this y into y minus 3 is greater than 0.0001, will increment. And after we break this condition, it's less than 0.001, that means we have a approximate solution of y. Okay. So y equal to initial value 0.001, and increment we already know, pi y times y times y minus 3. This is the 3 is okay. Let me also number is 3. So you want to compute cube root of 3. Okay. Minus 3 is greater than 0.0001. So this is our epsilon error. We will increase y by 0.001. Right. And after we reach this condition, after we break the loop, right, we approx number to the power 1 by 3 is equal to y. So here we also should take a mod operation, because this is mod operation should be taken. So mod is ABS function is there, absolute. Now it will do I guess we are overshooting. Wait, let me print the y as well here. Number equal to 3 by 20 plus greater than okay. So here we are overshooting. Let's see what should be the value exactly. 3 to the power 1 by 3. So 1.44 should be the value. I guess we have the increment should be more yeah, something like this. Okay, we reached the value. Yeah, we reached the approximate solution. And the error, let's say we want to also print the epsilon error. Epsilon error is with yes error this thing. Yeah. So with 9 into 10 to the 9.7 into 10 to the power minus 5 epsilon error, we are computing 3 to the power 1 by 3 as this. So let's say I want to compute 10 to the power 1 by 3. The value should be close to this, like 2.5, 2.15, something like that. Computer. Oh no. Here this should be number. So we are approximating 10 to the power 1 by 3 in up to how much? So up to 4 decimal point it is correct, right? And the epsilon error is 9.31 something into 10 to the power minus 5. If I want to make a more correct approximation, I should only reduce the epsilon error. Now see, now it is up to here, almost up to this decimal point. It is correct. 339. Let's add another 0 here. Now you see the increment is larger than the epsilon error. So, it approximates up to 334 here, up to 3 with an error of 1.399 into 10 to the power minus 7. So that's like really close. Okay, so the approximation solutions are there. So you can take let's say I want to use the epsilon error 1 0 here 0. Now I am to take 101 to the power 1 by 3. That would also how much time it will take for the months to take around, let's see. Okay, we should reduce the maximum number. So it takes too much time to reach until 101. Let's say we take 21. Now see, it's 50. And the solution is 2.7589. 2.7589. Okay. Cool. So 1 by 3 can be so 1 by 3 can be computed. X to the power 1 by 3 can be computed by this. Now the last algorithm we will be discussing is this Newton-Rephson, how you can generalize this a by b to the power p by q computation. So any type of, let's say, fraction to the power fraction, right? That can be computed. So in Python it's really easy. So we can also do something like 1.2 to the power 3.2, right? But algorithmically, how it is happening, how you can approximate this computation, we'll see. Just we will go over the Newton-Rephson first. Okay. So Newton-Rephson is something like this. Let's say, okay, let's do it side by side. That would be good. Okay. So we have to compute a by b to the power p by q. We don't know that variable. We don't know that value, right? Let's say that is x. So we have to compute x. Now, if I just change this, I can do like this, right? P x to the power q by p is equal to a by b. Now, x to the power q by p minus a by b is equal to 0, right? So now this equation, let's assume that to be f of x, function of x, and that is 0. So we have to find out a value for which this equation becomes 0, right? So let's assume the equation looks something like this. This is the point we want to assume. You say f of x equal to 0, and this is, let's say, x-axis, and this is f of x-axis. So you want to have this x value. right? And now we can start from any. So there are some assumptions that we have to start from a close point. Let's say where the function is changing its value, right? Plus from positive axis to, let's say this is positive, right? Positive value, and then this one is negative value. So there are some assumptions that we have to start in an interval where the function changes its value from positive to negative or negative to positive, because the root or the value where the function is 0 lies within that interval. So that would kind of reduce the um, reduce how many steps we have to go, or reduce or kind of specify which root we will find. Let's say one function is something like this, right? Let's say one function here, right? So here there are multiple roots. So in which interval we start, that actually specifies which root we will find. And the root finding mechanism for Newton-Rephson is something like this. Let's say we start here. This is our x0, initial guess of the root. So the corresponding projection in the function would be f of x0, right? And what you can do to get the next function, next x1, let's say x1 improved x, you can improve over the previous guess is by taking a tangent on that over the function on that point, right? And this would be what? This would be f dashed x, right? This tangent is f dashed x, and let's say we hit this point x1, and previously, see, okay, here. So here, what is the equation now? So f dash x is, so this is what? This is delta y, and this one is delta x, right? So f dash x is delta y by delta x, right? So so we'll just put all these values from the from this graph. So this is f dash x0, 0th point tangent. It will be f dash x0 is equal to delta y is f of x0 divided by this difference, x0 minus x1, right? Okay, so now we can represent x1 to be x0 minus f of x0 divided by f dash x0. Okay, so this is f dash x0. So this equation, this improvement equation can be generalized like this: x of n plus 1. So next guess is equal to x of n previous guess minus f of xn divided by f dash xn. Okay, so you can just loop over this equation until we reach this point. So the improvement should be something like this. So after we reach this point, we do the same thing. We get f of x1 here. So same, right? Draw a tangent, get x2. Same thing would repeat until we reach really close to the root. Okay. So this is until the f of x is, let's say, less than some epsilon ever. So you want f of x to be 0, right? So it will be less than 0.00001 or whatever close value of to 0 we want. We'll loop until that point. So here you see, to solve for x in this equation, we can do the same. We can do same method, right? We can just write the Newton-Rephson algorithm and put this function as f of x. The value of x would be computed, and x is what? X is a by b over p by q, right? Okay. So we just what was the function? F of x is equal to x to the power q by p minus a by b, right? Yeah, q by b by a by b. Okay. Now what would be the x dash x? X dash x is q by p x to the power p by p minus 1, and this one is because we are derivating across x, so this one is 0. Okay. Okay, 1 minute. We cannot do this, right? We are you see, we are doing p by q, right? So x to the power p by q cannot be computed, right? So we have to take a different approach. See, a by b equal p by q is equal to x. Now we can say uh, a to the power p, b to the power p is equal to x to the power q, right? So you just split the equation. So instead of taking q by p, because this one cannot be, so we are assuming that x to the power p by q cannot be computed, right? Or you can, yeah. So we'll split the equation like this. Now it will be b to the power p x to the power q minus a to the power p is equal to 0. So this would be, so all these are whole numbers, right? A, B are whole number. X we don't have any assumption at till this point. Q, P, these are all whole numbers. So this can be the power function can compute themselves, right? Okay. So it's like now it's the function. If this f of x would be b to the power p x to the power q minus a to the power p. F dot x is equal to b to the power p q x to the power q minus 1. Okay, and because q is an integer, q minus 1 should be also integer. Okay, now you can let's say start from any initial x and try to reach this the root of the equation. So let's compute this. Equations are this. Let's say a equal to, let's say I want to compute this 1 by 2, 3 by 2. So a is what? A is 10, a is 12, b is 10. So now a by b becomes 1.2, q is 32, and sorry, p is 32, q is also 10. So now what we are computing, a by b to the power p by q. So this should be the result, right? And if I just want to print this, print here p by b to the power this is what we are trying to do. Another form would be this is also the same thing. So the equation should be, so what is f of x? F of x is b to the power p x to the power q minus a to the power p. So b to the power p x to the power q, let's bracket in, And because these are integers, we assume that the power function can itself compute them. Star x to the power q minus a to the power a to the power q. So this is f of x, right? F of x is this, and f dash x is what? B to the power p q x to the power q minus 1. So b to the power p q times x to the power q minus 1. We have to bracket this q times q to the power, and this one will be nothing. Okay. So f dash x, and so given a value of x, let's say x x equal to 0.001, we can compute f and f dash, right? F of x function at that point is this, and the slope is this at that point, right? So now, so you already know that the value should be close to 1.79. So let's say we start from 1. Let's say we start from 1. Its initial value is 1, right? Now what I can do, while f of x, f of the function itself is greater than the epsilon error 0.0001, right? I can compute those two things and improve the value of x. So x improved will be x equal to x minus f of x divided by f dash x, right? So it will improve the value of x. Yeah. Now f of x at the end is what? See, 3 into 10 to the power 3 into 10 to the power 34 plus 34 minus 3 into 10 to the power 34. Okay. Absolute of because it's already print the x as well. Print x. Okay, we are kind of the guess is too far. Oh no, we already reached that point. We already reached close enough. Let's increase the epsilon error a bit. Not yet happening. It's already reaching the close value, right? 1.79 close. 7921. Yeah, 792137. Right, already reached that. So f of x, how much f of x? F of x. There are insignificant point I guess here. Okay, one thing you can also do is when the improvement is let's say not that significant, right? So what you can do, you can also check this fact. Absolute of this so the improvement that you are having is greater than this delta, then you will only there is no improvement. Oh no, that's not also. Go back to the previous one. Anyway, if I just run this, you see it reaches the root, it reaches the x value. This is the x value. And the value should, the desired value should be a by b to the power b by 2, right? So it is 1.21732235937. Yeah, it's almost correct up to here, right? One bit. Sorry. Okay. Okay, so this is how Newton-Rephson would work. Why it is not turning into data. So yeah, so today's agenda is up to here, right? So you can compute a by b to the power p by q. Also give approximate solutions to x to the power 1 by 3. So you see x to the power 1 by 3, instead of doing that increment method, right? That was really inefficient because we have to increment in 1 by 1, right? So the step size is fixed, but here the step size is kind of adaptive with respect to the slope. So it is more efficient. So Newton-Rephson will be more efficient than the approximation solution. So this one, so for search, binary search is efficient, and for computing any root of, let's say, this type of equation, right, it will be p by q. Newton-Rephson would be a better solution at this point. Yeah, with loops and normal if and conditions, you can program all these simple algorithms, which are kind of really useful in this one is really useful in computational mathematics, right? Yeah, and searching is always useful for, say, searching any key in a database or something like this. Whichever keys, let's say the keys are sorted, so binary search is the best way you can search. Okay. So at this point, these are the algorithms you can implement with loops and functions. Okay, so you will share the notebook with you. Yeah. Gunjan, you can stop, right?
If today's agenda is complete, then it's a good point to stop. And yeah, we'll just stop recording.
Okay. Okay then. Bye bye.